Thank you very much. Thanks to the organizers. Really enjoying this meeting. So yeah, this talk is going to be about two-dimensional turbulence above topography. There won't be any anti-diffusive behavior. However, it's connected to one thing that's mentioned on the website of this workshop, which is large-scale organizing principles, which is basically, can we design and use simple prescriptions to determine the large-scale flow that arises in a turbulent system, okay? The large-scale ordering. So I will discuss the condensation transition. I've had a great introduction by several people, including Alex, on how 2D flows tend to produce large-scale condensate. And I will then discuss forced-dissipative flows and how we can select minimum-enstrophy solutions to predict this large-scale condensate. Okay, so there are a few equations in this talk, but if you bear with me, I hope by the end of the talk you'll have learned this quite simple method to compute the large-scale flow, if you don't know about it already. Okay, so that's rotating turbulence above weak topography. So we're considering a single layer of fluid. It's rapidly rotating. Okay, so there is going to be mostly a horizontal flow that is independent of depth because of the Taylor-Proudman theorem, if you wish. So you can describe it as a rotating shallow layer of fluid. And the ocean floor here, if you're thinking about the ocean, is irregular. So you have bathymetry. So the local height is capital H of x, y, and t. And there's a reference height here, which is the mean depth h0. Okay, so shallow water equations, U and V are much less than W. And you can introduce the vertical vorticity here, dx of V minus dy of U. And you can show, starting from the rotating shallow water equations, that there's an exact material invariant in the system, which is called the potential vorticity Q. You can see it's the ratio of the total vorticity of the flow. You have planetary rotation and local vertical vorticity divided by the total depth here, which is a function of x and y. Okay, so that's a conserved quantity. And if you want to make progress, you can leverage the rapid rotation of the system to derive quasi-geostrophy. So because of rapid rotation, the main balance will be geostrophic balance, in which case the flow derives from a stream function psi, and mind the minus sign here in the GFD convention. And the vertical vorticity will be the Laplacian of that stream function. Okay, so this conservation equation for capital Q then becomes a conservation equation for this quantity little q here. So you can see the material conservation. This is just the total derivative of little q. Well, this is advection, written as Jacobian by the horizontal flow. And this potential vorticity q is the vertical vorticity zeta, so that's the Laplacian of psi, plus a correction due to the topography. Okay, and this topographic potential vorticity eta, you can see is directly proportional to the local bathymetry of the system, right? H of xy minus the mean bathymetry h0. So if you remove this term eta here, you can see you're just back to the standard 2D Navier-Stokes equation, right? That's material conservation of the vertical vorticity, Laplacian psi. And so the way topography is going to modify the system is just by adding here these topographic PV, this given field of x and y, in the relation between potential vorticity and stream function. Okay? So why would I do that? Well, there are several motivations, I think, to study this. One could come from oceanography. The topography at the bottom of the ocean is known to impact the mesoscale turbulence, that's vortices between 10 and 100 kilometers. It's known to influence this turbulence and also the large-scale currents in the ocean, such as the Antarctic circumpolar current that flows around Antarctica. And that's because, as a result of the topography, there is a strong stress applied by the current onto the ocean floor, and that's a way to remove momentum from this current here. At a more local scale, there are long-lived vortices that are associated with topographic features, such as the Zapiola vortex or the Lofoten vortex. So that's one motivation, oceanography. Another question could come from maybe statistical physics. We've had a great introduction from Alex, who's making the parallel between 2D turbulent flows and statistical physics, mentioning the various phases of turbulence and the phase transitions between these different kinds of 2D turbulence. And if you look at the next chapter, maybe in a book on statistical physics, the next question is, what is the impact of random disorder on a phase transition? Okay, so you could ask what is the impact of this random topography on the transitions that Alex has discussed, for instance. And one last motivation, which is really the main motivation for this talk here, is that historically this system of two-dimensional flows above topography has been used as a test bench to test a large-scale organizing principle based on variational approaches. And these two variational approaches are known as selective decay or entropy minimization in this context, and the statistical physics of 2D flows, and I will review what those two principles are. Okay, so that's really my motivation to try to understand these variational approaches, whether we can derive a large-scale organizing principle for this system. Okay, so let's start with selective decay. So the idea is fairly simple. It originates from plasma physics, and the idea is, well, you start with a turbulent system that has two invariants, okay, and some very weak viscosity nu. So you send nu to 0, but it's still here. And typically you'll end up with a dual cascade phenomenology, right, where one invariant is going to go to small scale, but the other invariant is going to go to large scale. And when you send nu to 0, well, the inverse cascading invariant will be conserved because it's at large scale and it doesn't feel the viscosity, whereas the forward cascading invariant will robustly decrease in the sense that it will be dissipated at a nu independent rate in the limit nu going to 0. Okay, something like the 0th law of turbulence or anomalous dissipation. Okay, so the selective decay recipe, then it's fairly simple. It's telling you that then you should minimize the forward cascading invariant while conserving the initial value of the inverse cascading invariant, right? So that's one recipe, which could end up being a large-scale organizing principle. All right, so for the problem at stake here, this boils down to entropy minimization. So this is the set of equations, right? Material conservation of this potential vorticity Q, which is Laplacian of psi plus the topography eta. And I've included a very small hyper-diffusive term here. Okay, so if nu equals 0, there are two conserved quantities for this system, right? You could multiply the equation with psi and average horizontally. This would go away. This is 0 here, and you would get conservation of the energy grad psi squared, right? Kinetic energy of the flow. You could also multiply this equation by Q and average horizontally, and you would get material conservation, you'd get conservation of this entropy here, which is defined in this problem as Q squared. Okay? So now, based on the dual cascade phenomenology, you think, well, if I start with stuff here at some intermediate scale, then the entropy will be transferred to higher wave number and will be robustly dissipated by nu, regardless of how small nu is, whereas the energy should go to large scales and will be conserved in the limit nu going to 0. Okay, so the selective decay principle then becomes you should minimize the entropy Q subject to a given value of the energy E, which would be the initial energy of the system. How do you do that? Well, you define a functional, here L, which is the integral of Q squared, okay, so that's capital Q, and you include the Lagrange multiplier to conserve the energy in the system. Okay, so you want to minimize Q subject to conservation of the initial energy of the system. You minimize that with periodic boundary condition, and once you solve the variational problem, you end up with this minimizer where Q, which is Laplacian psi plus eta, is simply proportional to the stream function. The constant of proportionality being the Lagrange multiplier here. Okay, so there are various enjoyable properties to these fields. First of all, there's steady solutions to the equations. Okay, if you look at this equation with nu equals 0, if Q is a function of psi, then this nonlinear term vanishes, it's steady, so you have 0 here, it's indeed a solution to the equation. Moreover, if this solution is indeed the absolute minimizer of the entropy, then this solution is going to be stable, according to Arnold, and that's because since you've minimized the entropy, if you had a small perturbation, that you'll have a tiny bit of entropy, but you're still close to this minimum, and you cannot go far away from this minimum because that would require more entropy, and entropy is conserved, so you don't have more to get away. Okay, so you'll be stable according to this criterion. And here, there's just this mu here that I haven't specified, but the way you determine mu is once you get psi following this relation, you can compute the energy and express mu in terms of the initial energy of the system, and so you have a well-defined psi without unknown parameters. Okay, so that's selective decay. There's another rather similar approach, which is the statistical physics of 2D flows and geophysical flows. I think it was popularized in geophysical fluid dynamics by Rick Salmon, who considered only the energy and entropy invariance, whereas strictly speaking, if you look at the evolution equation for Q, any moment of the potential vorticity is an invariant of the system without dissipation. And then in the 90s, it was extended by Miller, Robert, and Sommeria to account for all these invariants. Again, there's a nice review here if you want to learn about that. But then, again, for most practical applications, users of the theory end up restricting attention to energy and entropy as the only invariants of the system, in which case statistical physics of 2D flows boils down to Q should be proportional to psi with some proportionality constant. So the two variational approaches to determining the equilibrated state of the flow boil down to a Q being proportional to the stream function. Okay? All right, so maybe there's one point in favor of selective decay as opposed to a statistical theory where you would conserve energy and entropy, which is that if you run the system numerically, you do observe that entropy does decay. Okay, and so I've been very much inspired by this paper by Leah Siegelman and Bill Young, where they consider exactly this problem. Their topography has a spectrum that goes like k to the -2. It's a slightly rough topography. They have no forcing or dissipation, and they only include some sharp filtering at very high k, which can be seen as a very strong form of hyperdiffusion. Okay, and here's what they see. This is the dimensionless entropy as a function of time, and that the different colors are different initial values of the energy. Okay, so what you can see is that entropy does decrease quite a bit during the simulation. This is a log scale here. So there is a strong decrease in entropy, which is a point for selective decay, I guess. However, they also claim that the end state of these simulations is not the minimizer of the entropy. And those are fields of Q here that they get at the end state of their simulations. So that's for a low initial energy. And what you should see here, there is a large-scale faint background here, which is compatible with entropy minimization, but you can also see these very strong vortices that actually saturate the color map here, and these vortices are pinned to the topography and they're not predicted by entropy minimization. When they run the same system with higher initial energy, they got a similar situation, but instead the vortices would roam freely within the system. Okay, and they identified a threshold energy of the initial condition. So that's an energy because eta here is time -1. It's a topographic potential vorticity. And below that E sharp, you have pinned vortices. Above E sharp, you have roaming vortices in the domain. Okay, so that's what they say. All right, so here are a few questions. In this talk, I will be considering the same system here, but now potentially with a forcing on the right-hand side, large-scale friction and hyperviscosity. So in the ocean context, this would be the curl of a wind stress here that's driving the flow. Here you would have Ekman friction, maybe, and then some hyperviscosity. And I will restrict attention to topography eta that is at a scale, or several scales, that are strictly smaller than the domain scale. I don't need scale separation, but I want it to be smaller. So there's the topographic scale, and then there's the larger scale of the domain. Okay, so the questions will be, first consider the energy-conserving case, where you have no forcing, you have no large-scale dissipation, and you're sending nu to 0. One question is, can we further characterize the transition in Siegelman and Young? And more precisely, how do we connect that to what we know about 2D turbulence without topography, namely that it should produce a large-scale condensate in some range of parameters, and specifically when the topography is negligible, right? Then I will switch the forced-dissipative case with non-zero forcing, non-zero large-scale damping, non-zero hyperviscosity. And the question is, well, can we predict the equilibrated state in this case based on selective decay or the statistical mechanics of 2D flows? Because these variational approaches, they were designed for the conservative system that conserves energy, yet real systems have a source of energy and dissipate energy. And I'd like to see if we can still derive a large-scale organizing principles based on these approaches to conservative systems. Okay, so the outline of the talk would be a first part on the energy-conserving case, and I will discuss the transition to large-scale condensation in the system. I will first review the Bretherton and Haidvogel, I should have mentioned their names. They are the first ones who studied entropy minimization in the context of 2D flows above topography. So I will review their solution before introducing a new branch of solution that exhibits a large-scale condensate, and I will compare that to DNS. And then I will switch to the forced-dissipative case, and I will show you how, while in this system, we end up with a continuum of solutions with the solution being indexed on the initial energy of the system. Here, you can select a single solution out of this continuum of solution based on the forcing and large-scale dissipation that you have in the system. Okay, so we'll do that through an asymptotic expansion, and then I will consider small-scale forcing and large-scale forcing, showing you how we can make predictions for the large-scale condensate in these two cases. Okay, so let's start with the energy-conserving case and revisit the minimum-enstrophy principle of Bretherton and Haidvogel. Okay, so that's what we obtain from minimizing entropy, right? That's the solution to the variational problem. And this is easily solved in Fourier space, right? This is linear in psi. So you can go to spectral space. The hat here is the Fourier transform, and the Laplacian is just minus k squared. So psi hat of k is just eta hat of k divided by mu plus k squared. Again, at this stage we don't know mu, but we can express the energy as grad psi squared and invert this relation to get mu in terms of E. Let me show you how that works for a monoscale topography, which I will use as an example throughout the talk and also to make the direct numerical simulations. Now, that's not a necessary assumption, it just makes the computations easier. So for monoscale topography at a wave number k eta, the Laplacian of eta is just minus k eta squared times eta. So psi becomes eta over mu plus k eta squared, this times in real space, because the Laplacian of psi is also minus k eta squared times psi. Okay, from this expression of the stream function, I can compute E, I can compute Q, right, the energy and the entropy. You get this expression for the energy, this expression for the entropy. We don't really care about the details. The idea is that from this expression, you could extract mu in terms of E, insert mu in here, and the prediction you would get is the entropy Q as a function of the energy E of the initial condition in this on this entropy minimizer. Sorry. So you can introduce an energy scale here that is based on the root mean square, the variance of the topography and the wave number of the topography. You introduce a dimensionless energy over E eta, and this dimensionless entropy is just the square root of E tilde minus 1 squared. This is this blue curve here. Okay, that's just one prediction, Q as a function of E, but once again, you know the entire field psi, right? So that's what Bretherton and Haidvogel did. And I'm about to claim that this is all fine, but this is not necessarily the absolute minimizer of the entropy. Okay, indeed, there's another way to solve this variational problem here. So let's go back to this equation here and now consider, for now, that mu is going to be minus k0 squared, where k0 is the gravest mode, the gravest wave number of the domain, okay, 2 pi over the domain size. Why would I do that? Well, because if this mu is minus k0 squared, you can see that this operator on the left-hand side is not invertible anymore, right? It has a non-zero kernel where you have sine k0x, sine k0y, any combination of those. So the solution now to this equation should look like psi eta here, which is similar to the BH branch that we've computed. It's the same solution, except that mu has been replaced by minus k0 squared. But now you have this solution here to the homogeneous equation. So there is a large-scale solution here that's a harmonic function at wave number k0. Laplacian k0 equals minus k0 squared psi 0. And I chose it to be normalized to 1. Okay, and then there is an amplitude here, which I will refer to as the condensate amplitude. Because indeed, if you look at psi eta here, this is a small-scale stuff. This is at scale k eta of the topography, but this is a large-scale condensate at the domain scale. Okay? Remember, on the BH branch, we didn't know mu, and we got mu from the energy, from the value of the energy E. Here we know mu, but we're going to get A now from the value of the energy. Okay, so right, the energy of the system is grad psi squared, and that's an expression that involves A. So now I can invert that to get the expression of the dimensionless amplitude of the condensate here, made dimensionless using the domain scale wave number and my energy scale. Okay, and in the limit of scale separation, not that I need it again, but it simplifies the algebra, I get that A tilde will be plus or minus the square root of E tilde minus 1. Okay, so we get a quantitative prediction for the amplitude of the condensate, and you can see it's valid only if E tilde is greater than 1. This looks like a standard supercritical bifurcation, and the threshold value of the energy would be E tilde equals 1. Okay? So this is what we've got. Here is the amplitude of the condensate as a function of E tilde. We've computed this branch here with a condensate, the amplitude of which is simply the square root of E tilde minus 1. And below 1, there is no condensed branch, and so the system should be on the BH branch of solutions. Okay? So my interpretation of this is that to some extent, the topography acts like a reservoir of energy. So you can host a small-scale flow of energy up to E eta, which corresponds to E tilde equals 1. Okay? When there's excess energy as compared to E eta, this excess energy is going to spill out of the reservoir and follow the standard condensation behavior, and so it will end up in a large-scale condensate. That's what you get here. Okay? I haven't computed explicitly the entropy associated with this condensed branch, but you can do it. And here's what you get. So remember, this is entropy as a function of energy for the BH branch, and that's the new branch of condensed solutions, which I've shown here for a topographic wave number, which is 12 when non-dimensionalized by the domain scale. And what you can see is that indeed the condensed branch of solution corresponds to entropy that is much lower than the BH branch of solutions. So if indeed we follow the selective decay principle, then the system will seek to reach the absolute minimizer of the entropy, so it should be on the BH branch all the way to E tilde equals 1, above which it will go to the condensed branch. Okay, so that's the prediction. We can compare that to direct numerical simulations. I've run pseudospectral DNS on a GPU. The topography is at K eta equals 12, which I will use for all these examples. So it's rather small scale topography. The initial condition is typically at largish scale. I consider K equals 3, something like that, and I start with some psi at K equals 3. And there's very weak hyperviscosity, and I check that the results are independent of the low value of the hyperviscosity. Okay, so qualitatively first, this is the stream function obtained at the late time of the simulation. Here that's for a low energy, below the energy threshold for condensation. And indeed, psi looks like a small-scale flow at the scale of the topography. Whereas if I initiate the simulation with an energy that's greater than E eta, here E tilde is greater than 1, I do see a large-scale condensate here at the end time of the simulation. So qualitatively, this is all very compatible with what I've said. Yet, if you look at the potential vorticity Q, you can see that indeed there are these isolated vortices, which are the vortices described by Siegelman and Young. They're pinned to the topography and they are not predicted by selective decay at all. Okay? So if you look at the faint background here, you can see there is red stuff here and blue stuff here, which corresponds to these two vortices. And that's the part that's correctly predicted by selective decay. But then you have these isolated vortices that are much stronger on the one hand, but on the other hand, they occupy a very small fraction of the domain. So will they affect the condensation transition or not, is the question. Okay, at least if we're planning to derive a large-scale organizing principle, then maybe we don't care about that, and the condensate will be predicted accurately. So quantitatively, I've run a suite of numerical simulations varying the energy of the initial condition. Okay, I've considered two types of initial condition. These crosses are just psi at K equals 3, like I said, and phi is an initial condition that is tailored to be close to the entropy minimizer. Like the small-scale flow is the one you expect, plus large-scale perturbations. Okay, the theory, once again, is the solid line here. And you can see that, indeed, the numerical data points are aligned quite well here on the prediction. There's a bit of scatter here near the threshold for condensation. Okay, so this might be reminiscent of the Siegelman and Young vortices, which are affecting the near threshold behavior. Okay, but overall, this seems to be very good agreement considering how simple the algebra was. Okay, so it seems that selective decay does have skill as a large-scale organizing principle. We can look at the entropy in these numerical simulations as a function of the dimensionless energy. And you can see that indeed the data points are fairly close to the BH branch, not too close, especially near threshold. That's these points here. And above the threshold for condensation, well, indeed, the entropy is much less than what would be predicted by the BH branch, and it reaches this condensed branch of solution. Okay? So that's the conclusions of the first part of the talk. I've studied the energy-conserving flows, okay, in a square domain with a smaller scale topography. I've derived a continuous transition to condensation as I vary the initial energy of the initial condition. And I've predicted this transition using entropy minimization, and it seems to be in very good agreement with direct numerical simulations. Okay, so it seems that selective decay, or the statistical physics of 2D flows, because after all, both of them predict that Q will be proportional to psi. That seems to be a powerful large-scale organizing principle, even at a quantitative level. Okay, so I was happy about that, but at some point you have to realize that real flows are forced and dissipative, right? Be it in the lab or natural flows, so they receive energy from an external source and they dissipate it. So that's an out of equilibrium situation, and I was wondering whether we could use these variational approaches that were designed for conservative systems in this out of equilibrium context. Okay? So one way forward is to consider small forcing and dissipation. Right, so you still have material conservation of potential vorticity Q, but now on the right-hand side you have weak forcing, weak friction, and weak hyperviscosity, and Q is still Laplacian psi plus eta. Okay, based on this small parameter epsilon, you can start an expansion. So eta will be just eta 0, order 1, or epsilon to the 0, right? And then we're going to expand psi as psi 0 plus epsilon psi 1 plus etc. Q is Q0 plus epsilon Q1 plus etc. And I'm going to introduce a slow time variable, capital T equals epsilon T. Okay? You substitute in the equations and you collect terms at order 1. You just get the set of equations we had before, right? That's material conservation of potential vorticity Q0 advected around by psi 0, and Q0 is related to psi 0 through what we had before. But now we know solutions to this problem, right? Using selective decay, we know a continuous branch of solution, and that's the condensed branch of solution. Okay, so if we assume for brevity that the system is on the condensed branch, then psi 0 will be the small scale flow psi eta plus some large scale condensate, the amplitude of which is now allowed to depend on the slow time variable, capital T. Okay, and I would like to have an evolution equation for this condensate amplitude. So the standard approach would be to go to the next order and write a solvability condition and get the evolution equation of for A of t. You can do that, but I think a shortcut is just to write the energy power integral, right? The energy is input by the forcing and dissipated by friction and hyperviscosity, and you just substitute the expressions of these quantities to lowest order. Okay? Gives you the same answer, and you get an evolution equation for the amplitude of the condensate here, which, to some extent is reminiscent of a normal form for the amplitude of the condensate here. Okay, so there is time evolution of the amplitude of the condensate squared here. You have damping here due to friction, damping due to hyperviscosity. You have nonlinear damping that's going to saturate the condensation instability in the system. And now the forcing enters through these two Grashof numbers here. So the first one, Grashof eta, involves directly the correlation between the forcing and the small scale topography, whereas Grashof 0 involves the correlation between the forcing and the large scale structure of the condensate. Okay, so there's two ways the forcing can drive condensate in the system, either through its correlation with the topography or through its correlation directly with the large scale structure of the condensate. And I will consider both situations independently. So first, if you have topographic-scale forcing, right, so f psi 0 is 0, the forcing is at the scale of the topography, and this one is non-zero. Then this is what you get for the equation. You can see this forcing term here, there you have damping, and here nonlinear saturation. And you can compute the solutions to this. This is a simple pitchfork bifurcation, or it looks like it, plus or minus square root of Grashof minus a critical Grashof number, which is just 1 plus this ratio of the two diffusive mechanisms. Okay, so I guess the simple case, if nu is really very small, even as compared to eta, this would be 0, critical Grashof is 1. Okay, so I've tried that numerically by including forcing, and I've considered two cases, a forcing that is directly proportional to eta to maximize this correlation between forcing and eta, and then to test the robustness, I've considered the forcing that's proportional to eta, but I'm also adding this psi, which corresponds to another realization of eta, which is independent of this one, of this small scale stuff, so psi is uncorrelated with eta. Okay, I've taken values for the dissipative coefficients, small values, but this ratio ended up being 0.28 for what I did. So the critical Grashof number will be 1.28. And this is the numerical data as a function of these Grashof numbers. You have the amplitude of the condensate as a function of Grashof. The prediction was a supercritical bifurcation like that. And indeed, the data point seemed to be very close to the prediction, and even the threshold is quite well predicted here. Okay? So that's one limiting case. The other limiting situation we can consider is when the forcing is at large scale, okay, domain scale forcing. So now I consider the opposite limit where the forcing is at very large scale, so it's correlated with the large scale structure of the condensate, but it's uncorrelated from the topography. Okay, in that case, I've considered very small nu for brevity. So what I have on the right-hand side here is these linear forcing or linear growth rate, and then the saturation here due to friction and to nonlinearities. Okay, so the steady solutions to this equation are slightly different. This is what you get, two solutions that exist only when the Grashof number is greater than 2. So that will be a saddle node bifurcation. Yeah, I'm showing it here. So I'm showing here this would be the Bretherton and Haidvogel branch, and then above a threshold value GR0 equals 2 for this square root to exist, to be real. You have this A plus branch, which is here, which will be the absolute entropy minimizer, so I haven't shown the A minus branch. Okay, and again, I've performed numerical simulations of the system. I've chosen the forcing to be proportional to cosine K0y, which is indeed the gravest mode of the domain, so there's non-zero correlation here. And that's the data points. So you can see that there's very good agreement above threshold here. There's a slight discrepancy here in the exact value of the threshold and maybe in the range of bistability here. And that, again, is probably due to the Siegelman and Young vortices, which we will see near threshold, but which seems to be wiped out away from threshold. Okay, so that's the conclusions of the second part. I've shown you how we can design a method to predict the equilibrated forced-dissipative flow by adapting the approaches that were designed for the conservative systems, so that's selective decay or the statistical physics of 2D flow. I've shown you that the continuous transition that we saw for the energy-conserving systems, it remains continuous for topographic-scale forcing, but it becomes discontinuous for domain-scale forcing, and yet the two bifurcations are correctly predicted using the same approach. We could validate that using DNS. So it seems that selective decay, or the statistical physics of 2D flows, they can be adapted into a large-scale organizing principle that also works for forced-dissipative systems. Okay, so that's all I wanted to tell you. I'm excited about trying to do that for other systems that have multiple invariants. That could be multiple fluid layers, continuous systems, go back to the MHD systems that motivated selective decay in the first place, etc. I'm happy to take questions.
Thank you, Basile. We have lots of time for questions. Neil.
So these small-scale vortices that are pinned to the topography, so they upset the original picture, right? So is that, or could that be understood by looking at the fact that the entropy is only one of more invariants?
Probably, and I don't know. Let's see, I'll try to show some pictures here. Okay. So yeah, one question is maybe there's another functional that could be minimized that is not simply the entropy, that is more, that implies the fourth order moment, maybe of Q or something like that. I don't know of any way to do that quantitatively and predict these states. Also, this seems to depend on the initial condition I start with, because so here you indeed have many vortices, and that's what you would get for these crosses here. if I start with an initial condition that is closer to the absolute entropy minimizer, I will end up exactly on the entropy minimizer without these pinned vortices. So there is some multi-stability here, and probably with very many initial conditions, I could get several values here. So I don't know, there's also this picture that I'm not quite familiar with, but I think in disordered system in standard statistical physics, you have this very complex energy landscape, and you can end up in metastable states that are not the absolute minimum, and it could be something like that that's arising here, but not being an expert, I cannot say more.
So another question on the small vortices. Your comment about the initial condition dependence begs the question, are these guys stable in the sense of Okubo-Weiss? You know, going back to the story of McWilliams centuries ago. And are they, then the question would be, what's special about the role of topography in that?
I don't know. Well, I can say they're surprisingly stable because basically I wanted to get rid of it and couldn't.
Well, chances are it's yes, I think, if you looked, right?
They're stable, and they're also, I should say, they're also observed for the Lofoten vortex. I'm pretty sure for the Zapiola vortex, maybe too. What they do observe is a small vortex that goes in the direction that would be predicted by such a pinned vortex, which is opposite to what you get if you just homogenize potential vorticity.
Well,
so they seem to...
That's the whole point of that story, right? That you don't homogenize.
Yeah.
Right.
So it seems, yeah, so I guess they're surprisingly stable. You don't homogenize, and yet when it comes to the large-scale structure of the flow, it seems you can safely discard them, but I don't know how much you can generalize that to other systems.
Okay, Pascal was next.
If I understand correctly, this should also apply in 3D as long as the 3D is only at the very, very tail end, really small scale end of the spectrum, right? There's nothing there that's specific to 2D as long as the 3D scales are really, really tiny, right?
Yes. Yeah, for instance, if we consider what Alex has described, right, where you have a range of scales that are predominantly 2D, and then you have the 3D structures, then yes. But for instance, it would be interesting to look at the system. You would conserve some form of energy, but maybe it would be only the energy that was input into the large 2D modes to begin with, or it's the energy that's part of the 3D modes will have a forward cascade and be dissipated. Yeah, good question. To some extent, yes, at the larger scales, and then I don't know how the three-dimensionality is going to affect the whole picture.
Okay, Grisha and Brad.
Could it be that without external forcing in this first regime, this is just non-ergodic? Namely, it just goes somewhere, in other cases, it goes somewhere else. When you add enough random forcing, you start exploring your phase space, and then you can really get where you want to go. Because 2D is notorious for its, you know, you can have may have a minimum, but your evolution won't get there because somehow it's non-ergodic. It does not explore enough your phase space.
Well, it could be, yeah, and maybe that's another way to say that the system is stuck in a metastable state, right? So it's indeed not exploring the phase space as much as I would like it to, because I know there is a more convenient absolute minimum, but the system doesn't want to go there. So yeah.
Could you say a little bit more about the higher order Casimirs? Some people like Peter Weichmann have emphasized their importance for conservation, and there's some numerical simulations now that conserve a large number of these. Maybe it's related to Grisha's question about ergodicity too.
Yeah, could I say more? Yes, probably. So indeed, you could decide to pick a different, well, you could try to conserve more quantities. What I'm worried about, and that's maybe why I put slightly more the emphasis on selective decay than on the statistical mechanics of 2D flows where you conserve all these invariants, is that, you know, as soon as you run that numerically, you see a robust decay of entropy at a rate that's independent of nu, and the same is true for the higher moments of the vorticity. So indeed, you can write equations with a small-scale term that are going to be designed to conserve some moments of the entropy. But really, if you start with standard viscosity and send nu to 0, you get this robust decrease of entropy and of higher order moments. So that's one part of the answer. The other part of the answer is, if I'm interested in the amplitude of the condensate, this seems to do pretty well. So, then it depends, do I want to make a much stronger effort, because it's probably difficult to try to capture this, knowing that this is also bistable and some initial conditions will just end here. But yes, if you want to characterize the small scale flow, then something else needs to be done probably.
So if I understand correctly, even in the forced-dissipative case, your system is actually very close to the entropy minimizer, right?
Yes.
But in the dissipative case, I would not minimize entropy, I would minimize entropy dissipation rate. And one of the things you cited was, I think, the Taylor paper, right? Where one minimizes the magnetic helicity but conserves the energy.
Yes, although don't they minimize the energy while conserving the helicity?
Yes, you are right. But you can get the same result by actually minimizing the energy dissipation rate.
Okay.
And not the energy itself.
Okay. I don't know about that, so I should. Okay. Yeah. Be happy to.
Edgar?
Is there an effect of the number of initial vortices in your initial condition with respect to the number of local maxima in the topography? I mean, in other words, if you have a small number of vortices initially relative to number of bumps and vice versa?
Yes, I think there is. So once again, well, first of all, you can see this multi-stability here, and it's related to the structure of the initial condition. I don't know if it's exactly the number of vortices, if it's something like that. Maybe one way to have this deride even more, I haven't started because I'm not, but if you start with a very, very small scale initial condition, that would have then very strong vortices at small scale, then yes, maybe you can maximize the number of pin vortices and derive that more.
And if you have too many vortices, you can't pin them, right? So some have to.
Yeah, so some of them will, a significant fraction of them will just merge or be distorted into small scale filaments that will be dissipated through the standard entropy dissipation mechanism. And what fraction remains pinned to the topography, I'm secretly hoping it's a small fraction, but maybe you can tailor an initial condition that will maximize this.
Yeah. So do you have any idea what happens for stronger forcing? So does everything fall apart? I'm thinking in standard QG, isn't the wind stress curl sort of formally order 1 effect?
Yeah, that I would have to check. And I should also say, as you saw, these are completely derived from the initial oceanographic motivation, so I don't know, to make progress. It's true, it's not, I don't claim to have solved the, out of equilibrium statistical physics. I'm just saying, if you're close enough to equilibrium, you can take into account forcing and dissipation perturbatively and still make predictions.
Yeah, fair enough.
That's all I know. If the forcing is strong, then, if the forcing is strong, we know that, you're going to get turbulent cascades of the type that Alex described. And no, we haven't solved that in the sense of...
David?
Could you just expand a bit on your last point about extensions to things like Taylor's constraint? I mean, Taylor's constraint is a very 3D argument from the beginning. You said about MHD at the end.
I did MHD. I didn't see Taylor. I didn't say Taylor constraint.
Taylor relaxation, sorry.
Could I
wonder what you had in mind.
Yeah, I'm not sure what I had in mind. I just had in mind I should really read those papers again and see what happens there. That's okay. That's the honest. That's the truth.
Okay.
Always a good start. Okay, let me check online. No? Okay, let's thank Basile again.